So in this lesson, we're talking about the normal distribution and z-scores. It says in the last lesson, we started to look at data that was approximately normally distributed. So that was data that kind of fell into that bell curve. This included marking values 1 and 2 standard deviations from the mean. So we had the mean somewhere towards the middle, and then we'd mark like 1 standard deviation away and 2 standard deviations away, and estimating the percentage of the distribution that fell 1 or 2 standard deviations from the mean. In the exact perfect standard normal distribution given by this function, and we won't spend a lot of time on it, but it's interesting because we see a lot of things from the course. We see e in this function, we see pi, which is kind of interesting. We see a quadratic. The same percentages or proportions of the data always fall within 1 and 2 standard deviations of the mean. This is true for any other section of the curve too. So we're gonna see that down the page a little bit. So this is that perfect normal curve right here. And basically, no matter what, if we make it perfect like that, we see that between 0, which is the mean, and 1 standard deviation away, there's always 34% of the data that fall between there. So you can imagine this as being like a bar graph that got flattened out into a curve. So back up to here, 0 stands for the mean of the data. The 1 stands for 1 standard deviation above the mean. The -2 stands for 2 standard deviations below the mean. So that's how it's labeled because those standard deviations away are important and they're our main focus for today. So now we're going to determine the proportion of scores that fall in the ranges below. So the first one is falls 1 standard deviation from the mean. So when we say within 1 standard deviation, okay, we're talking about from the -1 to the 1. So we're going to add up these 2%. So 34 plus 34 is 68. So in the normal curve, 68% of the values are 1 standard deviation from the mean. Our next one is 2 standard deviations from the mean. So we're going to add up all 4 of these numbers. And I'm going to write them all out. You could obviously, double some of them because they appear twice. So this adds up to 95. And that's a lot, right? So 95% of the data is 2 standard deviations from the mean. And then 3 standard deviations from the mean. Basically, if I look at this one, I'll write it out, but we're adding on 2 more 2.5s, so that adds up to 100%. And we'll talk about that in a second, but for now, we're just going to write down that 100%. So it's 100. So 100% of the data falls within 3 standard deviations from the mean. So some concepts to see here. Most of the values in the normal distribution fall near the mean. Okay, so the bars in the middle, they're symmetric, right? But they're always taller in the middle versus the sides. Okay, so stuff tends to be close to the average. The values above and below the mean are balanced, symmetric like we said. It is rare, less than a 5% chance, okay, to fall outside 2 standard deviations from the mean. Okay, so it's about 5% chance. So if I'm out here, right, that's rare. Okay, so if we talk about heights, it's rare to be super tall or super short. It's more likely that people are around average height. And we say that those values within, in that middle, in the white section, in here, are considered typical, common, or expected. The stuff on the outside we don't really expect. Now, if you look at this curve and you consider the fact that E is involved in it, these 2 sides of the curve don't actually ever come down to 0. So the reason this adds up to 100% is because these values, these numbers, are all rounded to the nearest 0.5. Really, if we look at the note, the percentages in the chart are rounded to the nearest 0.5%. The percentage of scores that are 3 standard deviations from the mean is really 99.8%. So the graph doesn't come down and touch 0, okay, in terms of the y direction. It kind of tapers off, but still almost everything is 3 standard deviations from the mean. So on the next page, test scores are often manipulated to be normally distributed. SAT scores are one example. I think I might have had something back on this page that I had to read. But yeah, there are many examples of real-world data that are approximately normally distributed. Physical measurements such as height, weight, shoe size, and intelligence are all approximately normally distributed, especially for large samples. So a lot of things that you can measure about people, in most ways, people are pretty close to average. And then as we go out further from the average, there's less and less. And then, so that was out of order, but test scores, like they make SAT scores fall so that most people are around 500 and then less and less as we head out to 200 and 800. So now we're going to talk about z-scores, and a z-score is just the number of standard deviations a particular data value is from the mean. So if the data value is above the mean, the z-score is positive. If a data value is below the mean, the z-score is negative. So these numbers here, the standard deviations, are actually z-scores. They're not the only z-scores because we can have decimal z-scores, but those are z-scores. So right now we are going to label the mean for this situation. It says the price of printers in the US are normally distributed, so we can use the normal curve, with a mean of 240 and a standard deviation of 50. So the mean, we know, goes in the middle. So I'm going to put 240 right here on the z-score of 0. And then we're going to label the 1 and the 2, the -1 and the -2. So to head in the positive direction, I have to add the standard deviation of 50. So this is going to be 240 plus 50 is 290, plus 50 is 340. I only have to go out to the 2. In the other direction, we're going to subtract 50. We're going to subtract the standard deviation, which is denoted by the -1. So this is going to be 190, okay, and this is going to be 140, okay? So we just labeled the mean and data values with z-scores of 1, 2, -1, and -2. So now it says the printer you eventually choose costs $340. What is the z-score for the price of your printer? So this first one's pretty easy because I can see the 340 and I can see that its z-score is 2. Okay, so then it says how many standard deviations above the mean was the price of your printer? So that's 2. That's what the z-score means. It tells me how many standard deviations I am from the mean. So these two are just different ways. A z-score, that is the definition of a z-score. Now it says another printer you are considering has a cost of $265, but you thought the quality was not good. What was the z-score of that printer? Okay, so you were considering it, but you didn't choose it. So if I look at my labeled numbers, 265 isn't on there. But we can start to do some fiddling. I know that 265 is going to fall somewhere in between the 0 and the 1. Okay, so it's going to be some decimal. And we'll start to now work towards a formula we can use for that. But I don't even really need a formula because if I think about it, 265 minus 240 is 25. And that's half of the standard deviation, right? So the standard deviation was 50. So it's halfway up. So my z-score is going to equal half. Okay, so that one wasn't too bad. It didn't fall on a number, but we could kind of reason through it. The next one says, what is the z-score for a printer that costs $110? And this is more difficult to answer. So now we're going to start to move towards the formula for finding z-scores. I kind of did it here. I'm going to go back to the last question. Okay, I did the value minus the mean. How far away am I? And then in my head, I divided that by 50. And I said, well, 25 is half of 50. So that's the z-score. Okay. So here we're going to set up that formula. We do value, and we'll have the formula on the next page and we'll use it. We do the value minus the mean. How far away are we? So we are 130 away, and that's negative 130. And we should have a negative z-score for 110. And then we divide that to say how many standard deviations away. So we're dividing by the 50. Okay. So that is going to equal negative 2.6. Okay, for the z-score. So we can see that would go right past the 140 here. If you randomly selected a printer from the store, is it typical for a printer to have cost $265, $110? Explain your reasoning. So remember, our cutoff for typicalness is within 2 standard deviations. These are values that don't surprise us. Okay, so the 265, we could say is typical. The 110 is outside of that typical range. Not typical, or we could write atypical. Okay, so these z-scores help us decide that stuff. So basically, 265 falls within 2 standard deviations of the mean. And 110 does not. Okay, 110 is outside or past that -2. Okay, so it would be atypical. So here's just a summary of important facts, and then we'll practice some more on the next page. Important facts about z-scores. We do the value minus the mean over the standard deviation, which is what we did with the 110 to find a z-score. A data value with a z-score whose absolute value is greater than 2, right? So kind of ignoring the negative sign if that number is greater than 2 is unusual or unexpected because those values occur less than 5% of the time. This cutoff of plus or minus 2 standard deviations from the mean is something that we will use or will be used in multiple situations throughout the unit. Data values within 2 standard deviations of the mean are considered usual or expected, or we just use the word typical on the past problem.